Okay, so the question now exists is what effect does the chain length and branching have on an alkene's ability or its molecules to attract each other? Okay, and it's fairly simple, and let me show you a little table. Okay, so what we have in this table is we've got different alkanes with the formula. Obviously, this is their the molecular formula. We have the boiling point here, the melting point. Okay, boiling point would be when I go from liquid into gas. Melting point would be when I go from a solid into a liquid. And then what phase is it at 20 degrees Celsius? Okay, and obviously we've said in the previous videos that we are going to look at three different things. We're going to look at the boiling point, okay, the vapor pressure, and the viscosity. Now, I also mentioned in the previous video that we know if the force increases between molecules, then the boiling point will increase. If the force increase in vapor pressure, then there would be less vapor escaping, reducing the pressure caused by vapor. So an increase in force decreases vapor pressure. And obviously all of this is vice versa. Viscosity is a substance resistance to deformation, and the bigger the force, the more it resists being deformed. So the only one that is inversely related is vapor pressure. Okay, so here we can see that, and we're looking at chain length. So we're literally talking about what effect does more carbons have on boiling point, vapor pressure, and viscosity. Now hopefully all we need to do is look at boiling point, and that will tell us whether the force is increasing or decreasing when I've got more carbons. Okay, notice the boiling point is negative 162, which means that methane at a negative 162 starts going into gas. Ethane is at a negative 89 degrees Celsius. Propane at negative 40 degrees. Butane is at freezing point. Okay, when water freezes, butane goes into a gas. Okay, pentane, only at 36 degrees Celsius does pentane go into a gas. So at room temperature, assuming room temperature is 20 degrees Celsius, okay, pentane is a liquid, while all of the carbons before him, the less carbons than 5, would be at gas phase, and therefore obviously the rest will be in a liquid phase, and at some point it's at 20 degrees Celsius at room temperature, they are solids. I can't remember which how many carbons. Point that I'm trying to make is that if we look at the boiling point increases as I increase the number of carbons, okay, which tells me that the number of carbons, when it increases the force between the intermolecular force between the molecules, which increases the boiling point. It decreases the the vapor pressure, and it increases the viscosity. Okay, viscosity. Okay, so if the number of carbons increase, then obviously the force increase, having these three effects. Now let me give you an excellent example. Okay, let's look at butane octane, and candle wax. Okay, so you're asking me why are you looking at candle wax? Because candle wax is C31H64. Okay, butane is more commonly known as lighter fluid, and octane we can is typically the fuel that we use in our cars. Okay, so petrol has a level of octane in it. Okay, now lighter fluid, you can imagine if you take a lighter and you were to press the little button. Oh, can I draw a lighter? Let's try. Okay, if this is a lighter, okay, you know, if you press down on the lighter, do you see what happens? You hear gas escaping from the container, from the canister. Okay, which means that butane is a fluid at normal room temperature. That happens when you at room temperature. It is a fluid, which means again that our that the forces that exist here is less than the forces we have in octane fuel, because we know that octane fuel is a liquid. Okay, that's how we get it into our tanks. Then we have candle wax, which all of us know a candle is a solid thing. Okay, at room temperature it's solid. So in order to get butane into a boiling point from a liquid to a gas, we need very little energy to add to this. In order to get octane, that's fuel, from a liquid into a gas, well, it's going to require a little bit more energy, but still not a lot. I know you know that when you go to the gas station, you can always smell the fuel. What is that? Oh, that's vapor pressure. Okay, you can smell. Vapor pressure is literally the fuel molecules that are escaping, and that is what you're smelling, the vapors from the fuel that's reaching your nostrils. Okay, candle wax is completely the opposite. When you can hardly smell a candle when it's nearby, so there's hardly any vapor pressure. Okay, so we can see, and at room temperature, a candle should be in a solid phase, which means it's got a very high boiling point. It's not even melting yet at room temperature, so it's not a liquid. And so I just think these are three very excellent examples of how and I never showed you this, but hopefully you figured it. Butane is 4 carbons, octane is 8 carbons, and candle wax is 31 carbons. Okay, so again, notice just how the number of carbons have influenced the state in which we encounter the substance. Now, why is this? Why do more carbons have this effect? Well, again, remember that it all depends on the attractive forces that exist due to different charges on the molecule itself. Okay, so at some point in the molecule, and give me a brief moment to just draw a slight molecule here, a hydrocarbon molecule, okay, with carbon and hydrogens. Okay, now at a certain time we will encounter our electrons at certain places. Okay, so I'm just going to draw some random electrons, and I'll obviously not do a very, very good job of it. But notice here at this point, I've got, and let me add a few more. Okay. Notice here at this point, I've got a clunk of quite a few electrons at this point here, while at this point I've got fewer electrons. Okay, so, and here I again have maybe slightly, here it seems more or less even, but here it is positive. Now imagine what would have happened if I didn't have this part of the structure. It's very unlikely that my electrons will group together. But the moment I had this part of the structure, okay, this part of the structure, now it is more likely. When I add more molecules, the probability that I will have clunks of electrons grouping together is more likely. So basically what we are saying is that the more surface area I have, the higher the probability of unequally distributed electrons. And that causes then, when there are more molecules to attract one another. And that is what causes this. So if I were to have another molecule, okay, as you can see here, maybe here we have a negative charge and there we have a positive charge. So since again we have a more likely chance in this case of getting this positive and negative, while here it seems a little bit more evenly distributed, yet at some point in this molecule it might have this unequal distribution, and at some point in this molecule it has an unequal distribution, which means that all of a sudden these two have an opportunity to attract each other. Okay, the more of these parts I have, the more likely I am to have another part where I have an unequal distribution, and yet this one as well. So as my chain increases, the probability, the chances of having an unequal distribution is increased, and therefore I've got a better chance of attracting my neighbors to myself. Okay, that makes very good sense. Now the very nice thing about this structure is also that it's very easy to connect these two to one another. I will just have to, and I don't know how to do this, but I will just have to do this, and then they can just move closer to one another, and they're very easy to connect because they're these straight structures. Now I mention that because that's not always the case when it comes to branching. So imagine I still have 4 carbons, but this time I have my carbons in this form. Okay, so there's my 4 carbons. That hopefully you can see is a propane, and a propane with 1 branch on number 2 carbon. And now imagine I have another one of these. Okay, and again I've just got a random distribution of my electrons in here. Okay, and maybe we can see, okay, here seems like a clunk. I actually did it nice and even, which wasn't a good idea. So here I've got a clunk giving it a slight negative charge, and here again it seems a little bit even, but there's a slight negative charge. Now I somehow need to move this molecule in order to connect at that point. Okay, and now my branch is getting in the way, and I can't get as close to there as I would want to. Okay, my branch is hindering me from getting closer. So now what happens when we look at branching, if we increase the number of branches, okay, we will have a decrease in the forces, okay, because the branches are not allowing particles to get too close to each other. The branch itself is getting in the way. I'm sure that makes sense to you. Okay, so the force is decreasing. When the force is decreasing, the boiling point is decreasing. The vapor pressure is increasing, which means more of the molecules can escape from the surface, and the viscosity Okay, the resistance to deformation is also decreasing because there's a smaller force keeping particles together in a form. Okay, so it's more easy to deform. So this is really very basic. It's going to apply to all of the organic chemistry molecules that we are going to look at. The same effect. An increase in the carbon chain increases the force, but an increase in the number of branches decreases the force. So even though I might have butane at a which is carbon 4 hydrogen 10, it will have stronger forces in it than we will have in, what is this? Let's try and remember. This is propane, but on number 2 we have a methyl. So this is methyl propane. Now methyl propane is still carbon 4 hydrogen 10, but methyl propane at room temperature is a gas at room temperature, while we've just seen that butane at room temperature, okay, but butane is also a gas at room temperature, but its boiling point is 0. Okay, this one, okay, it's called isobutane is its more common name, but we will call it methyl propane, and methyl propane has a boiling point of negative, well, let's round it off, negative 12 degrees Celsius. At around negative 12 degrees Celsius, it's already boiling. Okay, and while carbon 4 hydrogen 10, but butane is only boiling at 0 degrees Celsius. So yeah, you can see the branch definitely has an effect on the strength of the forces if we look at experimental evidence where they actually go and test this. Okay, so thank you very much for watching. I hope you have a better understanding of the effect that branches as well as chain lengths, carbon chain lengths, have on the forces and the strength of the forces that exist between molecules. And yeah, we'll see you in the next video where we'll look at alkane reactions. See you then.